Okay, ready? I got it. What's one of them? Okay, there are three parts to this chapter. Two are minor and one's kind of major. What's one of them? What's one of the parts? They said, why don't you call somebody else? See if they know. All right.
Is one of them like the mass?
We're getting there. The world of mass, you mean?
Yeah.
And then the world of charge, that goes together with atoms and ions and isotopes, right? So atoms, ions, and isotopes, the world of mass and world of charge, that's the bulk of this chapter. What's two of the minor things? Raise your hand if you know one more. Yes, what's one? Right, the periodic table, the parts of the periodic table, is that correct? Where are the metals? Where are the non-metals? Where are the semi-metals? Where are the alkali metals? Yes, no? Again, you don't really need me to teach this to you because there it is right there. As a matter of fact, the next page, see where the metals are, and the non-metals, and the semi-metals. See, we looked at that before, and then, so anyway, this is something you don't really need me to teach you, just learn it. This is the alkali metals. That's the far left-hand column. That's the most reactive, chemically reactive metals we know of. The next column is called the alkaline earth metals. Then we have a big blue box here. Does everybody see the big blue box? What are those called? What do you call these elements? They're metals, of course. Transition metals, you'll find out later in the year that sometimes they lose one electron, sometimes two, sometimes three. They might switch back and forth. They're transition metals. And then we have over here, these are some non-metals that don't ever, almost never react. What are they called? Noble gases. And these are the most reactive of the non-metals, and they're called the halogens. They all end in ene: chlorine, fluorine, bromine, iodine, acetine. And then the real periodic table, you would make a cut right here, push all this down, and put these two little rows right here. The real periodic table is quite long. But if you shrink it down to fit on a paper, you wouldn't be able to read the numbers. So they said, snip, like that. And this is 58, and this is 57. These come after lanthanum, and they act like lanthanum. That's why they're called the lanthanides, and some people like to call them the lanthanoids. Okay. Or these come after the element actinium, and they're called the actinides or the actinoids. That's it. So those are the names you have to know. Okay, that's pretty easy. There's one more. What's one more minor thing? Not super minor, but one more part of this chapter. And you already answered one, so I know you know it, but do you know it, Madeline? What's the other part of this chapter? Yes, the scientists, right? How did we actually know that there were atoms? How did we know that atoms are made of parts, okay? So we'll go to this page here. We'll start out with some scientists again, and I think the last time we met, we talked about cathode ray tubes. What in the world is a cathode ray tube? And you don't see them anymore, very much anymore, but everybody used to have a television that was kind of big and fat, and that was a cathode ray tube. They had, they're called electron guns, and everybody used to have a computer monitor. It was kind of fat. Maybe you didn't in your lifetime. Anyway, those are all partially evacuated. They're partial vacuums, and they're shooting electrons. They're actually very good vacuums. And anyway, somebody a long time ago, J.J. Thomson, they thought, well, I need to make one of those. I can't make it. I'll have somebody else make it for me. And so they had this made, and he said, you know what I really need? I really need some pieces of metal in there hooked onto some wires. And I want it all to be sealed in a glass container. And I want to hook it up to some electricity. Wow, why would you do that? Well, when he did it, a beam came out. It's called a cathode ray, because it came out of a cathode ray tube. Now, you're a scientist, you say, what is that? I don't know. It seems to be emitted from here, and it's going over to here. So you hook up a field, electric field, which is kind of like a magnetic field, and it has plus and minus. And then notice that whatever that beam was, it seemed to be repelled by the negative and attracted to the positive. Said, I don't know what this beam is, but it's made of something negative. Now, what did we eventually call these things? What did we call these things that were coming from atoms and they were negatively charged? Electrons. And so that's why we say that J.J. Thomson is given credit for discovering of electrons. All right, this is the next one. On the basis of his results, Thomson wondered why an atom must be what it must be like. Although atoms contain these tiny negative particles, he also knew that whole atoms are not negative or positive. Thus, he concluded that the atom must also contain positively charged to balance out the negative. That's pretty good thinking, isn't it? I mean, when I pick up something, I don't get shocked. It's not charged, it's neutral. But you're telling me you know that atoms have some part of them that's negative? Well, they better have something else that's positive, or else I'll be charged all the time. Now, unfortunately, his guy's name was also named Thomson. Okay, get careful here. It says here, another scientist pondered the structure of the atom. Was not J.J. Thomson, but what? William Thomson, also known as, Lord Kelvin. He had to do with the thermometer thing, didn't he? And he said, I have an idea, and I think I know what it is. I'm going to call it the plum pudding model. Now, I'm not from England. I've never eaten plum pudding. Has anybody been to England and eaten plum pudding? Okay, good. I haven't either. But here's what I thought. I have a bowl. It's got pudding in it. It's kind of thick, like porridge, okay? And then there's raisins sprinkled in there. You could even stir them up if you wanted to, right? And he said, I think that's what the atom is. The atom's like a big bowl of porridge, and that's the positive part of the atom. And then the raisins are like the negative part. And you did something to make those raisins pop off there, and that's what happened. And so that was the model of the atom for a long time. Now, I don't know if I gave this to you. Let's double check here. If I give you a picture, here it is. I did. I got this on the internet. And notice that Dalton, he might have thought that they were kind of like, who knows, just kind of like balls. All right. And then Thomson, this is William Thomson, said, no, I think it's like a plum pudding, and they're just kind of spread out evenly, and that's what an atom is, and they were very scientific about that. But then, here comes the most classic experiment you normally hear about in chemistry class, and it had to do, down here, it said here, here you go. If you had taken this course, chemistry course, in 1910, the plum pudding model would have been the only picture of the atom that was described. However, our ideas about the atom were going to change dramatically in 1911 by a physicist named Ernst Rutherford. This is called Rutherford's experiment. And he learned physics in J.J. Thomson's laboratory in the late 1890s. By 1911, Rutherford had become a distinguished scientist with many important discoveries to his credit. One of his main areas involved interest in alpha particles. Alpha particles are positively charged particles with a mass about 7,500 times that of an electron. In studying the flight of these particles through air, Rutherford found, what did he find out? Okay, here's the classic experiment right here. He found out that the particles deflected by something in air, and so he tried to do an experiment. Now, this is going to dramatically change what we think about the atom. This whole experiment would fit on this table right here. Okay, so let me show you what this is all about. Before Rutherford, there were these people, remember the Curies, Madame Curie, Pierre Curie? Okay, even before them, named Becquerel, and they had learned about radioactive elements. They learned enough to know, you know what, I think we've been hurting ourselves by being exposed to all this radiation, and they passed that on. I'm sure that all of them died earlier than they should have, because with all that radiation, they would have had a lot more chances for different cancers and stuff like that. Now, but what they did learn is how to be a little more safe with it too. So what does Rutherford do? Rutherford puts his radioactive rock, it looks like a regular rock except it's radioactive, and he puts it in a box. What kind of a box? And if you haven't read this, okay, I'm trying to help you, but it's lead. Now, lead is very dense. And if you put it in a lead box and it's thick enough, the radiation won't be able to come out and get you. Get it? Now, he wants it in that box, but he actually wants radiation to come out when he wants to control it. So he puts it in here, and he has a little door up here, a little lead door, and he can actually lift the door, close it, and when he wants, radiation will come out, or he can close the door and it won't come out. Okay, now I need your attention because I don't know how much science you already know about this. This radioactive material was giving off parts of their nucleus. The radioactive material, some of the element was actually changing into another element by giving away part of its nucleus. This is called an alpha particle. An alpha particle is 2 protons and 2 neutrons. So imagine something that's made of 4 pieces. It's going at a pretty good speed, and it can actually comes away from radioactive elements. It's called an alpha radiation, alpha particle. Okay, can I see the radiation? No. On The Simpsons I can, because in The Simpsons what they do is radioactivity can make certain materials glow. You get that? Now some radioactive materials will glow just by being in the air. It'll make the air around them glow. So I might be able to see that. But I couldn't see these alpha particles streaming. But they had found it in a chemical. I think it was zinc sulfide, I think it was. And when you put this radiation and you let it hit this chemical called zinc sulfide, it scintillates. Scintillates. There you go. Have you ever used that word in English yet? Oh, when I saw them come out in their evening gown, she was scintillating. You guys, that could be a good one for you, all right? She looks so scintillating. Scintillating means sparkling, glowing. Get it? Anyway, so what would happen is if you open this door and there's some zinc sulfide somewhere, it's going to make it kind of sparkle and shine. And hey, it tells me there's radiation somewhere. Got it? So what? Now what are you going to do? That's fun. What are you going to do now? Okay, he's going to do something strange. He has this piece of metal, and he coats it with zinc sulfide. You open up the door, scintillate, sparkle, sparkle. He even could go through here and actually, with a microscope, he could actually see and count how many scintillations per second, okay? Now what? Nothing big there yet. Now he's going to take a piece of gold. Now, I don't mean a bar of gold. It wasn't that thick. It was very thin. One thing about gold, it's very malleable. Think about mallets. Did you know there are people called gold beaters? They take a little piece of gold, they go like this, and they pound it and pound it and pound it, and it gets thinner and thinner and thinner and thinner. And you know what then they do? People with a lot of money, they put it on cakes. Gold leaf. They put gold leaf. Even when I was in high school, I bought this kind of a science book. It's sitting right there. I can see it right now. And on there, my name is written in gold. You know why? I wrote it. They gave us, that's when gold wasn't as expensive. They gave us a little tiny piece of gold leaf. I put it down there. I thought it was pretty neat. I wrote my name, peeled it off. It was pretty neat. Wait. So gold leaf is really thin gold, but it is solid. It's solid gold, but it's thin. Now here it is. Ready? You gotta be ready for this. He's gonna put a piece of gold in front of this beam. Remember, without the gold, scintillate, 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 and only in one spot. You get that? Now, he puts the page, here it goes. What do you think would happen to a laser if I did that? It would block it, wouldn't it? It would block it. None of it would get through. But guess what he saw? He saw almost as many scintillations as he did when the gold wasn't there. But he saw some scintillations he hadn't seen before over here, back here, even back here. He couldn't quite figure this out. He said, it can't be plum pudding. The atom cannot be like plum pudding. Then everyone, and by the way, an alpha particle, this is where you have to pay attention. An alpha particle is made of 2 protons and 2 neutrons. What charge would an alpha particle have? If you're 2 protons and 2 neutrons, what charge would you have? Positive. These little bullets that were coming out, they were positively bullets. Now, if this was the case, and you try to go through plum pudding, and the whole pudding is positive, wouldn't all of them be deflected? It'd be deflected all over the place. Here's a positive plum pudding, around like that. Anyway, almost every one of them went straight through. He said, there's only one way I could explain that. most of the atom must be empty space. No one has said that before. Most of the atom must be nothingness. And I think there's a nucleus. That's the first time anybody mentioned that the atom had a nucleus. And that nucleus is incredibly small. And the nucleus is positively charged. Because when my positive charges, most of them went straight through and nothing happened. But if they get close enough to the nucleus, positive bullet, positive nucleus, deflect. Some of them mean deflect straight back. That changed the model of the atom forever in chemistry. So this guy's name is Rutherford, and again, the more you read about this experiment, you're going to understand a little bit more. And then last, I'm going to finish up the scientist. Okay, it said here, those alpha particles that scored a direct hit on the nucleus, in Rutherford's mind, it's only explained of the nuclear atom, the atom with a very dense center of positive charge called the nucleus, around which tiny electrons moved in spaces that were otherwise empty. He concluded that the nucleus must have a positive charge to balance out the negative charge of electrons, and it must be incredibly small and very dense. What was it made of? He concluded that the nucleus contains what he called protons, positively charged particles. Proton has the same size of charge as the electron, but it's positive. Rutherford reasoned that the hydrogen atom is a single proton at the center and one electron moving through space a relatively large distance from the nucleus. And this is the one everybody forgets because they barely mention this person's name. And this will be the last scientist we have. It says here, later in 1932, James Chadwick was able to show that, hey, the nucleus has to have more than protons in it because it's heavier than we think it is. So there must be something in there with no charge, but it still has a mass like a proton, and he was given credit for discovering the neutron. Well, there's all of your scientists right there in this book. Okay, and I showed this to you a few days ago. Whenever you draw a model of an atom, it's usually to terrible scale. The real scale might be like this. Here's the entire atom, including electrons. If that's 10 to the minus 8 centimeters, that's already small, isn't it? But how big is the nucleus compared to that? 10 to the minus 13. That's 5 powers of 10. That's 100,000 times smaller. The diameter of the nucleus is 100,000 times smaller than the diameter of the atom. Most of the atom is what then? It's empty. It's nothing, empty space. Everybody get it? And that's even today in elementary school, they teach about a nucleus and things like that. All right, I'm going to put the book up for a minute now, and I'm going to get to, like I said, the bulk of the chapter. And I think we finished the world of mass. I know we did. And we were getting into the world of charge. Did we get kind of into that a little bit? All right, so here's where we kind of almost finished this story. On this side of the brick wall is, in the atom, there are things that have charges. And I looked it up, and I don't memorize this number, but 1.6 times 10 to the minus 19th coulombs of charge. And wow, the proton also had that same charge, but one was plus and one was minus, and I'm a human, and they were human. And they said, I hereby declare that many coulombs equals one package of charge. You get it? So you're plus one proton, and electrons, you're minus one. And that's what we say. That made it easy, didn't it? That's easy. Now we go down to this model right here. I noticed there are 3 protons. Have we done this yet? Have we gotten this far yet? I don't have it written here. This is E class. So when we get down and look at this Bohr model, I'm not going to talk about neutrons. I'm not going to talk about neutrons in the world of charge. They're big in the world of mass, but not here. So I'm looking at 3 protons, and I see 3 electrons. What does that mean? What would you call this? And what if you have no charge? What if you're an atom that has no charge? We call you an atom. Some books like to say you're a neutral atom. Ever get that? Now, unless I tell you, if I ever see a symbol, if you see a symbol like this, Fe, if I don't tell you that I'm not neutral, then you're to assume it is. So I'll tell you something right now. Fe is number 26. I happen to know that that symbol says I have 26 protons. Now, since it's neutral, it would also have 26 electrons, wouldn't it? It would have 26 protons, 26 electrons. Uranium, number 92, 92 protons, 92 electrons. Yeah? So let's go over here now. Metals have a tendency to lose electrons anyway. Let's pretend that my lithium atom lost one of its electrons. Okay, now, ready? Yeah, I was with I was with one of those guys the other day, and we were at a bar, a salad bar. That's a salad bar. And I said, what's happening? You look kind of depressed. And he says, yeah, I think I lost one of my electrons. I said, are you sure? I'm positive. Anyway, so what happened is, as soon as a neutral atom loses one of its negative things, it becomes positively charged. And I'll show you how that works. We have we have 3 protons, but now I only have 2 electrons. Now it's not a neutral atom anymore. It's actually a charged atom. And we have a name for that. And look over here in the upper right-hand corner. If I put nothing there, if you see nothing, it means something. If you put nothing there, it means I have no charge. How can you have no charge when I know you have 3 protons? Well, you must have 3 electrons. But what about this guy here? What if he loses an electron? What am I forced to write? Here, I'd be right, here's lithium, and if I see nothing here, it's neutral. But what if this guy only has 2 electrons? Then I'm forced to tell you. I have to tell you, this is not a neutral atom anymore. It's called an ion. This is called a positively charged ion. You get that? You can be a negatively charged ion too. I'm trying to see if is this sinking in a little bit? Notice I'm not talking about the world of mass. I'm talking about the world of charge right now. All right, so now let's go down here. How much can you actually tell me about this symbol? Are you ready? What's one thing? Did we do this the other day? Okay, let's go down. Yes, give me one thing, Noah. Okay, so in this case, there has to be one more proton than electron, right? So the protons are ahead by 1. Now, how many protons do you have? So if I know I have 11 protons, and you tell me the protons are ahead by 1, so how many electrons? 10 electrons. Anything else you can tell me? Somebody else. Something else you can tell me from this symbol. Who didn't normally talk? Danielle. Tell me something else you can tell me.
Its mass number is 24.
Yes, so it has 24 things in the nucleus. So its mass number is 24. There's 24 things in the nucleus. How many are protons? And how many are neutrons?
13.
Right, so see, 13 neutrons. Wow, I can tell all that. I can tell it's sodium. Is that right? So that's what they're doing. They're trying to tell you all about this atom with these different corners. And the last but not least, the lower right-hand corner would be, what if I were going to make a compound, like you'll learn how to do this. Have you ever heard of these? H2O? You've probably heard of that. Yeah. Okay. In the lower right-hand corner, it tells you how many of those atoms are in that compound. There are 2 H's, and understood, they don't ever write the 1. Water really is H2O1. There's 2 H's and 1 O. This guy here has 2 sodiums, 1 oxygen. And that's what the lower right-hand corner, that's for compounds. You get that? And we're going to have a whole chapter on that. You're going to learn how to write thousands of compounds. We're not going to actually write thousands. I'll teach you how to write thousands of compounds. Okay, let's go to the next page. Now, we're going to jump down here. And here's our story, okay? Here's one of the biggest stories in chemistry class. Are you ready? Here we go. I'm going to start with lithium. And I'm going to start with chlorine. And what would happen if I were to take some lithium and bring it in contact with chlorine? I can promise you right now, I would not have to heat it. They would instantly, spontaneously react. And we do know that metals, and is lithium a metal? You have to be able to look at the periodic table and know, see lithium? Is lithium a metal? Most of the periodic table is a metal, isn't it? Lithium's a metal, and metals tend to lose electrons in a reaction. And what is chlorine? What would you classify chlorine as? Metal or non-metal or semi-metal? Non-metal. Non-metals tend to gain electrons in chemical reactions. You'll use that idea all year. You might as well remember it now. So what happens if I put them together? Believe it or not, lithium tends to lose an electron and chlorine tends to gain one, and chlorine will rip it off of you. It'll rip that electron and send it right over there. So let's take a look at this. Before I put them together, lithium had 3 protons and 3 electrons. It was a neutral atom. Before I put them together, chlorine had 17 protons. That makes sense? 17 protons and 17 electrons. It was a neutral atom. Yes? Okay, now, when I put them together, this is called chemistry. When I put them together, the chlorine will rip electron away from sodium. You say, well, lithium, I mean? Well, you say, so what? Well, then lithium now has 3 protons, but only 2 electrons. So lithium becomes a what? And this is where you got to turn your brain, twist it a little bit, because when you think about losing things, you think about negative, don't you? You got to twist it. If you lose one of your negative things, you become what? Positively charged. Okay, now, we have a special name for that. It's an ion, but it's called a cation. Now, you can always tell somebody who has taken chemistry who has not. If they've never taken chemistry, they call that cation. Cation! Okay? If they've taken chemistry, they know that's called a cation. I like to write the word cation with a T that looks like a plus sign. That reminds me that cations are positively charged ions. One more time. Metals tend to lose negative electrons in a reaction. They become cations. Now, let's go over here at chlorine. Chlorine used to have 17 protons, 17 electrons, but now what? Now what? 17 protons, 18 electrons. What's that add up to be? -1. Whoa, you're a negatively charged atom called an ion. And what's the name for that? Anion. Look, a negative ion. That's my memory trick for that. A negative ion. Anion. Nonmetals tend to gain electrons and become more negative and become anions. And here's the biggest part of the story right here. Here's the biggest part of the story here. Ready? I know in middle school you use some of these words, but I don't think you knew what you're talking about. Now I'm ready to use those words and see if you know what they're talking about. I lost one of my electrons and I became a positively charged ion. I gained one and I became even more negative. I was used to be neutral, now negative. Explain, why would chlorine and lithium react to form lithium chloride? It's going to form a compound called lithium chloride. Why? Let's think about it. If I lose an electron, become a positive ion, you gain it, become a negative ion, then what happens? Why didn't lithium say, well, I want to lose that anyway, see you later. Oh, I wanted to gain one anyway, see you later. But you know what? They're stuck. They're stuck together and they're bonded together. And what kind of a bond? Now here we go. What kind of a bond? What's the name of a bond that holds ions together? What kind of a bond would hold negative and positive ions together? Ionic. See, I don't think you knew really what an ion was in 8th grade. You might have memorized an ionic, says ionic compound, ionic bond, when there's a complete transfer of electrons. There was a complete transfer of electrons, right? You became an ion. I became an ion. I can't get away from you because of attraction. Positive attracts negative, right? Is everybody with me on that? What kind of a bond holds ions together? All right. What kind of a compound is made of ions? Ionic compound. Also called a salt. I know you know one salt. The only salt you know at home is table salt. That's NaCl. This is a salt. Lithium chloride is a salt. Any metal and any non-metal makes a compound. That's a salt. What about rubidium fluoride? That's a salt. I wouldn't eat it, but it's a salt. A salt is an ionic compound. You got that? Yes? Okay, one more time. What are ionic compounds made of? Starts with an I. Ions. What kind of bond holds them together? Starts with I. Ionic bond. And what do you call a compound that's held together with ionic bonds? It's called an ionic compound, also known as a salt. All right, see if you can do that. Answer this. Explain why chlorine and lithium react to form lithium chloride. And here you go. Lithium chloride is a blank compound. What kind of compound is it? It's ionic. Held together by what? Ionic bond. And is made up of ions with opposite charges. Maybe for the first time, you might understand a little bit what's going on there, okay? Now, in biology class, you would have met mainly carbon, hydrogen, oxygen, nitrogen. Non-metal, 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 non-metal. You wouldn't have had ionic bonds. Not with those. And what they do is, I want to gain. I want to gain. I want to gain. No, I want to gain. Well, how can we both gain? Why don't we share? Why don't we share electrons, and then we can both have them part of the time, and that's called a covalent bond. They cooperate with a covalent bond. This is not sharing. Hey, let's share the electron. No, I'm ripping it off your face, and you're not getting it back. We're not sharing anything. I'm taking it, I'm becoming an ion, you're an ion, and we can't get away from each other. There's no sharing going on this. That's called a covalent bond. Not this one. All right. What do you think? Getting pretty good at this? All right. What time is it? We will start this, but I won't be able to finish today, I can tell. 2:05. All right. Let's play a grid game. All right? Let me show you how to play the grid game, and I'm going to have some people come up, and they're gonna play the grid game up here on the camera. All right. Let me get a periodic table for you. If you need a periodic table, I have one right here. So if I call you up here, and let me show you how to play the grid game. All right. Here's how you play the grid game. I will write down something. For example, I'll write this right here. And there we go. I'll do that. And here's how you play the grid game. All right. I made a little checklist for you, and normally you would do the alwayses. Now I made that up, so if you can become a famous chemist, you don't have to say to somebody, don't you know what the alwayses is? Okay, here are the alwayses. These are things that are always true, always. Here we go, number one. I don't look at that number, I look at a symbol right there. See capital C? Capital C will always have what atomic number? It will always be number 6, always. And the reason you are number 6, if you're atomic number 6, it means you will always have 6 protons. Everybody with me? Ding ding. I just finished the alwayses. Now, if you start with the alwayses, then you can take a choice. You want to be on this side of the brick wall, world of mass, or the other side of the brick wall? I don't really care. After you do the alwayses, you can do either one. Let's do, which one? Pick, I don't know, Carolyn, pick, you want to do world of charge or mass? Which one should I do first? Mass? Okay. Where do I get information about mass? In the upper left-hand corner. This isotope has a mass number of what? 12. Does every carbon atom have a mass of 12? No, that's why he's not an always. This one has a mass of 12. That means there are 12 things in a nucleus, and 6 of them are protons. So guess what? It's just a coincidence that there had to be 6 neutrons. What's 6 plus 6? That's it. Now, I'm actually done with the world of mass. Now I crawl over that brick wall, and let's do the world of charge. Where do I get information for that? Right here. I don't see anything. What does that mean? You have no charge. Well, how in the world can you have no charge when you got 6 protons? You have to have 6 electrons. See that? That's how you play the grid game. Everybody see that? All right, so we're going to call some people up. Let me go ahead and get some of these ready. Okay, we might be able to get that much done today. All right, this is where it's fun for me. Here's what I like. You know who I want to go up there? The person I want to go up there is somebody you said, I am not 100% sure how to do that. And if you'll do this for me, and you say, I'm not 100% sure, when you get done, you're going to say, I feel a whole lot better about it. I don't want the person who says, I got this. I don't want you to go up there right now. All right, let's have a volunteer. Somebody raise your hand, okay? Said, you know what? I am not 100% sure. You have to take a chance. You say, I'm not 100% sure. I'm willing to go up there, and you told me when I get done, I'm going to feel better about it, all right? All right, who wants to go up there? Elizabeth, are you 100% sure? No. Okay, thank you. You did the right thing, Elizabeth. Oh, Elizabeth, did you know I didn't tell you all the rules? Darn, I should have told you all the rules before I had to go up there. The rules of the grid game are, you're not allowed to write any number on that paper unless you tell everybody in the class how you know that number there goes there, okay?
Okay.
All right, so what do you want to start with?
I guess mass.
I wouldn't. You know why? I'd start with the alwayses.
Okay.
If you start with the alwayses, you're going to be in good shape.
Okay.
What do you know is
So
always true?
the atomic number,
For what?
carbon,
Is what?
6.
Always?
Yes.
Right? Elizabeth, is it always 6?
Yes.
That's correct. Go ahead.
And the number of protons is always 6.
For carbon?
Mm-hmm.
Always?
Yes.
You sure?
Yes.
Okay. You check off, there you go. Now what do you want to do?
Mass number. It's 14.
Wait, is it always 14?
No.
Is this one 14?
Yes.
How do you know?
Because it's right here.
Okay. Very good.
And
Have you done the
then,
world of mass yet?
no.
Okay.
The number of neutrons would be 6.
How do you know that?
Because there has to be 6 because there is, wait, no, it would not be 6.
Ah,
It would be 8
how do you know that?
because it has to be 14, add up to 14 and there's 6 protons.
What has added 14?
The neutrons and the protons.
Ah, that's good. Are you done with the world of mass?
Yes.
How about the world of charge now?
There will be,
What's the charge on this guy?
not sure, or there's no charge
How do you know?
because it doesn't say right there,
Where are you looking?
right here.
Not there. Upper right-hand corner.
Yes.
Yeah, upper right-hand corner for next to carbon. I don't see anything there, do I?
Mm-mm.
That's no charge. How can you have no charge when you have 6 protons?
You have to have 6 electrons.
Excellent. Excellent job. All right, look at this. All right, do you feel better?
Yes.
Hey, did I tell you? I'm looking for somebody who's not 100% sure. You are not 100% sure. I have some harder ones for those people who are already sure. I have some harder ones coming up. But let's say you just, I'm not 100% sure. Raise your hand. I can almost promise you, you're going to feel better by the time you get done. Come on. Who's not? Who's not 100%? What do you got? 90? 80?
I'm 100%.
100%. Good. What do you got?
20%.
100%? Okay. All right. Who else? You're not at 100%. What do you think, Ty? You at 100? No? This is harder. This is harder.
I'll do it.
All right, go ahead. Go ahead, Ty. Thanks. All right, now listen, I'm listening to every word he says, okay? And that's what you need to do. Listen how he says it. All right, how you gonna do this, Ty?
So I'm going to start with the atomic number.
I would do the alwayses first.
The always things.
You can get messed up if you don't do the alwayses first.
Okay. And
Well, you
then
know it's always true.
the atomic number in protons.
What is it?
11
For anything?
for the yes.
For any element?
No, just for sodium. Or
Okay, so sodium is always, atomic number is 11?
yes.
Okay.
So it would be 11 and 11.
Wait, you know, number of protons is for sodium is always 11? Always?
Yes.
Always?
Always.
Okay.
Always.
Check that box off.
And then I'm going to do mass, and then I get the mass number from the top left.
Okay.
So it's 24.
Is it always 24 for sodium?
No, just this one.
For this one?
Yes.
This isotope? Okay.
Just this one. And then neutrons would be 13.
How do you, you're not supposed to write that till you tell everybody how you know that.
Because the mass number is 24, and
What does that mean?
there's 24 like protons or neutrons in it, and we already know there's 11 protons.
Ah.
So there has to be 13.
Those add up to be the mass number.
Yes,
All right, you done with the world of mass yet?
I am. And then the charge is the number of electrons is 10,
How do you know that?
because there's a positive charge.
What does that mean?
There's more protons than neutrons.
How many more protons?
1.
That's why it's plus 1?
Yes.
So you have 11 protons, how many electrons?
10.
Very good. Very good. Very good. Do you feel better about now?
I feel amazing.
Very good. All right. How about somebody else? One more person, then I'll change the game a little bit. One more person. So just not I'm at 90, but I'm not 100%. You know, if you make a mistake now and fix it, it's much better than when you take the test and act like you don't know what you know. Whoops. All right, Kayla, go up here. All right, you're gonna do it. You must be 100% sure because you did not raise your hand. You talked to your sister about, did she see me the other day?
Yeah.
You both of you, I mean, it's really cute, you know, family. All right, here we go. How are you gonna do this? What do you wanna start with?
Start with the always.
With what?
The always.
Oh, what, okay, like what?
The atomic number
For what?
for hydrogen.
Okay, so what is the atomic number for hydrogen?
1.
Always?
Yes.
What if it was an isotope of hydrogen?
I don't know.
No, it's always
Okay.
1 for hydrogen. Well, wait, what if it was an ion of hydrogen?
Still be 1.
It's still 1. That's why it's called an always. Now what?
It has the same number of protons as the atomic number.
Always?
Yes.
Even if it's an isotope of hydrogen?
Yes.
Now put a little check over there with always, so
Okay.
you got those done. Now, which
Yep.
world do you wanna go into?
I guess the world of mass.
Okay,
So it would be 3 because of
what is the mass?
the mass number of the
What is the
hydrogen.
mass number?
3.
What?
3.
Always for hydrogen?
No.
No. Is this one 3?
Yes.
Okay.
And then neutrons would be 2 because
And what now?
neutrons would be 2
Because you have to add the number of neutrons and protons.
Yes? Okay.
Okay. And then you do the world of charge,
Yes?
and that would be
It's like a soccer game, the pluses versus the minuses.
mhm,
Who's ahead? Pluses or minuses?
the pluses.
They're ahead by one, aren't they?
Yeah. So it would be 0. Okay.
Wow, no electrons. Wait, do you feel a little bit better about this now?
Yeah.
Thank you. All right. Okay, what do you think? We're running out of time. Here's what I'd like to do. If somehow you have not been doing your homework, remember the homework is the last half of this packet, isn't it? You should be able to do quite a bit by now. You could almost finish the packet. Okay, so make sure you're working on your homework, and I will not see you until Wednesday. All right, so you got plenty of time to get some stuff done. Thank you.